Good evening everyone, good evening. I welcome you all again to the NEET Elite. Hope you guys are doing great, having the good time. Well guys, let me know in the chat box if I'm audible and visible to everyone. Let me know in the chat box if I'm audible and visible to every single guy. Just give me the thumbs ups if I'm audible and visible to everyone. Right? Perfect. Perfect, guys. Good evening, welcome guys, welcome back to the NEET Elite, right? Perfect, I'm doing wonderful guys, I'm doing wonderful. How are you all doing? All right. Okay, so I got the green signal from Priya, is that? Thanks for giving me the green signal. Alright guys, so as you all must be knowing, today we are going to continue with the General Organic Chemistry, and it's going to be the lecture number 10 of General Organic Chemistry. And in the today's session, we are going to talk about something called as hyperconjugation, yeah? Okay, one of the important topics from the General Organic Chemistry part, okay? The session is going to be very short and precise, okay? We are going to start and finish the concept which are involved in the effect hyperconjugation, right? Perfect. So before starting the session, let me introduce myself. As you must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. So people, for the ones who have not liked the video yet, please do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Okay, so let me know in the chat box if you guys are super duper excited for the session. Let me know in the chat box with the thumbs ups if you are super duper excited for the session. Let me see the josh of the session as I used to see. Yeah. Well, John is saying josh is extremely high. That's great. That's great. I'm doing great, Aisha. I'm doing great. I'm doing perfect. Yeah. All right. I can see a lot of thumbs ups are coming up. That means actually you guys are super excited for the session. Okay. So without wasting a lot of time, let's get started with something called as hyperconjugation, okay? So people, what is this hyperconjugation all about? I hope you remember, we started with the inductive effect, then we talked about resonance, then we talked about mesomeric effect, and now it's the time, and then we talked about aromaticity, definitely, yeah? Okay, and now it's the turn for the hyperconjugation, okay? Well, let's talk about its definition. As per the definition of hyperconjugation is concerned, it is the delocalization of a sigma bond adjacent to a pi bond. What does that mean? Before making you understand the definition of this hyperconjugation, let me tell you, this hyperconjugation, it is shown by highly polar bonds only, okay? And what are these highly polar bonds? We have got the examples of the highly polar bonds as CH or CX bond, where X is the halogen right here. This CX and CX bond, these are considered to be highly polar bonds, and the hyperconjugation which I'm going to talk about in some time, okay, that is shown by this CX or CH bond, which are considered to be highly polar, yeah? That's why your CH3 group and your CX3 group, right, these are going to show the hyperconjugation effect, right? So first thing which I want you guys to take a note of, which is important, this hyperconjugation effect, okay, this hyperconjugation is shown by highly polar bonds like your CH bond, like your CX bond, okay? That's why CH3 and CX3 are the groups which are going to show the hyperconjugation, okay? Now let's get in detail of what this hyperconjugation is all about. Let's talk about its definition in detail, right? So as per the definition is concerned, it is the delocalization of a sigma bond which is adjacent to a pi bond. Let's get to know this definition by simply taking a molecule right here. I have taken an alkene right here, okay? Which you can see right here. It is CHHH, this is CH, this is double bond, this is CH2. It is one simple alkene right here, okay? Well guys, this is a pi bond right here, correct? And this is a sigma bond right here, and this is one more sigma bond right here, okay? This sigma bond I'm talking about, and this pi bond I'm talking about right here. This pi and this sigma, okay? Well, hyperconjugation, it is the delocalization of this sigma, okay, which is adjacent to this pi right here, okay? So let's get to know its actual thing, let's get to know its actual thing by means of valence bond theory and molecular orbital theory. What this delocalization of sigma bond, which is adjacent to pi bond, is all about. Let's get to know this a bit more in detail in terms of valence bond theory, right? Well, guys, let me tell you, this carbon right here, if I ask you about the hybridization of this carbon, you are going to tell me its hybridization is sp2. Okay. What about the hybridization of this carbon right here? It's again sp2 hybridized carbon. Yes. What about the hybridization of this carbon right here? It is simply sp3 hybridized carbon. Okay. Let me make its proper structure by means of valence bond theory. Let's consider this carbon first. It's sp2 hybridized. Okay. See guys, this is one sp2 hybridized orbital, this is one more sp2 hybridized orbital, and this is one more sp2 hybridized orbital. First of all, I'm talking about this carbon right here, okay? And I made 3 sp2 hybrid orbitals of this carbon right here, okay? So with these 3 hybrid orbitals, this carbon is going to have one p orbital like this. This is the p orbital of this carbon right here, okay? Similarly, if I talk about this carbon, this is again sp2 hybridized, okay? So let me make the structure of this carbon as well. So it's going to be one sp2 hybridized hybridized orbital of the another carbon. Yes, it's going to be one more sp2 hybridized orbital. This is one more sp2 hybridized orbital, right? And it's definitely going to have one p orbital like this. Okay, so can I say right here a sigma bond got formed between two carbon atoms? Yes, this is the sigma bond which I'm talking about. Okay, this is the sigma bond which I'm talking about. And people, since this is a p orbital, this is one more p orbital, both are parallel to each other, they are going to form a pi bond. Yes, they have formed the pi bond as well. With this carbon, you have got 2 hydrogen atoms attached. So let's say this is one hydrogen atom, this is one more hydrogen atom. Yes, okay. Now guys, at the same time, see, this carbon right here, it is sp3 hybridized, okay? So if it is sp3 hybridized, I would have to make 4 sp3 hybrid orbitals of this carbon right here. Yes? So people, have a look what I'll be doing. Let's assume this is one sp3 hybrid orbital of this carbon. Okay, there will be one more sp3 hybrid orbital like this. There'll be one more sp3 hybridized orbital like this. There'll be one more sp3 hybridized orbital like this. There is not going to be any p orbital with this carbon right here. Okay, so which bond is this one right here? This is again a sigma bond. This again is sigma bond. That means I'm talking about this bond. Yes. And people, understand one more thing. We have got 3 hydrogens which are attached right here. Okay, this is one hydrogen attached, this is one more hydrogen attached, this is one more hydrogen attached. Okay, if I consider this single bond, this sigma bond right here, okay, between carbon and hydrogen, I'll say carbon is more electronegative, due to which electron density will lie more towards carbon. Electron density will lie more towards carbon right here. Okay, now people understand, this sp3 hybridized, this sp3 orbital and this p orbital, this sp3 orbital and this p orbital, they are going to show the overlap. This overlap between sp3 orbital and pure p orbital is something which I call as hyperconjugation. Yes, so let me represent it with a different color right here. So this overlap I'm talking about between sp3 orbital and p orbital, this is something which I call as hyperconjugation as per your valence bond theory approach. Okay, so I can define hyperconjugation like this. It is the overlap between sp3 and pure p orbital. Okay, the overlap between sp3 and pure p orbital is something which I call as hyperconjugation. Okay, similarly guys, at the same time, this sigma bond would have, this can also overlap with the, this sigma bond if I consider between carbon and hydrogen, the electron density is going to be towards carbon. Even this sigma bond, even this sp3 orbital and this p orbital, it's going to overlap. Even this sp3 orbital and this pure p orbital is going to overlap, right? Everywhere, whenever you see sp3 p overlap, it's going to be called as the hyperconjugation. So let me know in the chat box if you got the concept of what this hyperconjugation actually is all about through valence bond theory approach. Can you let me know fast? Can you let me know fast? Can you let me know in the chat box so that I can show you one more approach, that is molecular orbital theory approach? Yeah, is it clear to everyone? Let me know fast. Yeah. Perfect guys, perfect. One more thing. Can I say due to this sp3p overlap, this bond is going to weaken? Yes, this bond is going to weaken, and this bond, I mean this pi bond, it will simply break in this direction, and this bond, it's simply going to break in this direction. Yeah, that's something which I'll be telling you in some time. I'm going to make you understand how to draw the proper hyperconjugating structures in some time. Since one thing I want you guys to remember, since it's going to be sp3p overlap, which is not very much effective, right? Extent of sp3p overlap is very, very less, right? But due to this overlap, I'll say this bond is going to get weakened and this bond breaks in this direction. Okay, that's why there will be in one of the hyperconjugated structures, there'll be negative charge on this carbon, and H positive is going to remain attached to this, H positive right here, it's going to remain attached in the vicinity of this molecule right here. Okay, or I'll say something like this. This electron cloud right here, it is going to attract this H positive over here, which I'll be showing you in some time. Okay, this was one approach to understand the concept of hyperconjugation, which was the valence bond theory approach, right? Now let's get to know the same hyperconjugation in terms of molecular orbital theory, right? Understand what I'll be saying. See guys, let me draw the same molecule again. This is carbon, this is hydrogen, this is one more hydrogen, this is one more hydrogen, yeah? Over here I've got a single bond between carbon-carbon and this hydrogen. This is double bond, and as you can see right here, this is CH2. Yes, this is CH2. If I talk about the hybrid, if I talk about this hyperconjugation in terms of molecular orbital theory, how will I be making you guys understand this? Have a look. Have a look, guys. Understand properly. See, this is first of all a pi bond right here. If it is a pi bond, that means this is basically right here pi bonding molecular orbital, right? Because bonding molecular orbital always remains between the nuclei of the two atoms, right? So this pi bond, it's formed by the pi bonding molecular orbital right here. Okay. At the same time, if this is the pi bonding molecular orbital, it's going to have pi star as well, which I call as, and pi star matlab, which I call as anti-bonding molecular orbitals, right? Pi star, yes. And you all must be knowing, you'd have studied in chemical bonding, I guess, right? You'd have studied these anti-bonding pi molecular orbitals. They do not lie between the nuclei, they lie away from the nucleus, right? Now guys, understand. See, this is the sigma bond right here between carbon and hydrogen. Can I say this sigma bond can show overlap with this empty, with this vacant pi star anti-bonding molecular orbital right here? This is the anti-bonding molecular orbital, right? And this overlap between sigma and pi star right here, this overlap between sigma and anti-bonding pi molecular orbital is something which I can call as hyperconjugation as well, yeah? So people, I can say hyperconjugation is also sigma pi star anti-bonding molecular orbital overlap, right? So this is also something which I call as hyperconjugation, correct? So in terms of molecular orbital theory, what is hyperconjugation? Hyperconjugation is sigma pi star overlap. In terms of V.O.T.E, hyperconjugation is sp3p overlap. Let me know in the chat box if it is clear to everyone so that I can move ahead and talk about this hyperconjugation a bit more in detail. Let me know in the chat box. Let me know in the chat box fast. Yeah, perfect. All right, so people, this is as per what? This is as per your molecular orbital theory, okay? And as per your V.O.T.E, it's going to be sp3p overlap, right? This is as per V.O.T.E, correct? Now let's get to know the concepts which I'll be using in the questions from the topic hyperconjugation, okay? Let's get to know. See guys, this is something which I told you right now. This hyperconjugation as per your valence bond theory, it is sp3p overlap, or we call this as sigma p overlap. Or as per your M.O.T. is concerned, molecular orbital theory is concerned, it is sigma pi star overlap. That's it, right? Now guys, let me show you how the hyperconjugated structures are to be drawn. Okay, understand what I'm going to say. This is first of all, just a second. This is a pi bond right here, okay? And over here, this is the sigma which I'm talking about, right? Now, this this sigma bond is going to show delocalization right here. This sigma bond is going to show delocalization right here, okay? And people, this will come over here like this, and at the same time, this bond will be broken down towards this carbon, by means of which I'll get one hyperconjugated structure like this. This is carbon, this is one hydrogen which is as such, one more hydrogen which is as such. Now this H hydrogen, it's not going to leave entirely as H positive, it is still going to remain in the vicinity of the molecule. Yes, as H positive, correct? And over here you'll have a double bond, and right here as such it is CH, it's going to be single bond, it's going to be CH2, and with the CH2 you have got the negative charge right here. This is one of the hyperconjugated structures of this molecule, yeah? Now at the same time, this is also a sigma, this is also a sigma bond, right? Okay, let's erase this part, This is also a sigma bond between carbon hydrogen, this is a pi bond. So I can say this sigma bond can also show the delocalization. It can come in this direction and this will go in this direction. And at the same time, what is one more hyperconjugated structure which I'll be getting right here? It's going to be C, this is going to be hydrogen, this is going to be hydrogen, and right here you'll have H positive which will remain in the vicinity of the molecule as such. And this is a double bond right here, this is CH, this is single bond, this is CH2, and on the CH2 you have got a negative charge right here. Yes, so people, this is one more hyperconjugated structure over here, right? Similarly, there can be one more hyperconjugated structure, and you all will be knowing what that hyperconjugated structure is going to be. I'll take this hydrogen out as H positive, so I'll get one more hyperconjugated structure as, it's going to be carbon, this is hydrogen, one more H I'm keeping as H positive like this, and over here it's a double bond, this is CH, yes, and it's CH2 with a negative charge right here. Yes, this is one more hyperconjugated structure right here. So how many hyperconjugated structures are possible in this case? I'll say the number of alpha hydrogen is also always equal to the always equal to the number of hyperconjugated structures. What do we mean by that? See, understand what I'll say. See guys, if I talk about this carbon right here, can I say it's sp2 hybridized? Okay, the carbon which is attached to this sp2 hybridized carbon, this is right here sp3, okay? This sp3 hybridized carbon right here is what I call as alpha carbon, right? This I call as alpha position, right? And to this alpha carbon, how many hydrogens are attached? There are 3 hydrogens attached with this alpha carbon right here. So I'll say this molecule simply has 3 alpha hydrogens, and the number of alpha hydrogen is always equal to the number of hyperconjugated structures, which is 1, 2, and 3. Yes, right? Very, very simple. See guys, understand once more what I told you a few minutes back. I told you this carbon right here is sp2. The carbon which is attached to sp2 hybridized carbon, which is basically sp3 in nature, yeah, this carbon I'll be calling as the alpha carbon. The hydrogens which are attached to this sp3 hybrid carbon, I'll call these hydrogens right here as alpha hydrogens. The number of alpha hydrogens is always equal to the number of hyperconjugated structures. And remember, more the hyperconjugated structures, more is the hyperconjugation, more is the stability. Remember that at the same time. Yes? Right? Perfect, guys. Now, this is something which I told you, this is something which I've shown you, and this is something which I've shown you, right? We have drawn 3 hyperconjugated structures right here. Correct? Now, as I told you, number of hyperconjugated structures is always equal to the number of alpha hydrogens, correct? In the earlier case, which I've shown you a few minutes back, there were 3 alpha hydrogens. That means there were 3 hyperconjugated structures, correct? Yes? Now guys, understand one more thing. Understand properly what I'm going to say. See guys, in the brackets right here, this is a conjugated system which I have. This is a conjugated system, right? As it has got pi, sigma, and so on. So this is right here, the conjugated system. And with this conjugated system, I've attached the CH3 group right here, okay? Now what this CH3 is going to do right here. See guys, this is pi and this is sigma. Can I say over here there is a possibility of hyperconjugation? Yes, there is a possibility of hyperconjugation. So what is going to happen? Delocalization of this sigma bond is going to take place, right? In this direction, this bond will break in this direction. Similarly, this bond will break in this direction and so on. So due to the delocalization of this sigma bond, is the electron density inside the conjugated system increasing or decreasing? I'll say electron density inside this conjugated system is increasing due to the delocalization of this sigma bond, okay? And any group which increases the electron density due to the delocalization of the sigma bond, in the conjugated system, we say that group shows plus H effect. Okay, so that group which increases the electron density in the conjugated system through the delocalization of the sigma bond, okay, we say that group shows plus H effect, right? So this is basically the CH3 right here, it's basically showing plus H effect. Yeah, right? Absolutely. Now guys, one more thing. Hyperconjugation, it does not operate at meta position. Okay, hyperconjugation, it does not operate at meta position. Why is that? What do we mean by this statement? Understand properly what I'm going to say. In order to make you understand this statement right here, let me take one more molecule. This is one more molecule. I have attached CH3 group on this benzene ring. Yes. So what is going to happen? Ignore this arrow, guys. Ignore this arrow. Okay, ignore this arrow, right? So we will, right here, I'll say this is a conjugated system. This benzene ring, it's a perfect conjugated system, right? There's a typical example of the conjugated system. And with this conjugated system, I have attached this CH3 group right here. Yeah? Now what is going to happen? Can I say this is pi and this sigma, this pi and this sigma is going to show delocalization right here. Yes. Can I say over here hyperconjugation is possible? Yes, hyperconjugation is possible. How come? See, this CH bond, it will break in this direction, and at the same time, this double bond will break in this direction. So what is going to be my first hyperconjugated structure right here? It's going to be carbon, and this hydrogen I'm going to attach as such. This hydrogen is as such. This H positive is still going to remain in the vicinity of the molecule as H positive. Yes, and there will be a double bond right here. Okay. And at the same time, what is going to happen? Since this bond has broken in this direction, so there'll be negative charge over here at this position, okay? And right here double bond, right here double bond, I'm doing nothing with them. Yes, they are going to remain as such, correct? Okay. Now we will at the same time understand one more thing. Can I say when this negative charge got created at this ortho position right here, can I say this negative charge is in conjugation with this pi bond right here? It is pi sigma negative charge with a lone pair. Can I say it's again going to show resonance right here? Yes. And due to the resonance, this negative charge will come here. Yes. Due to the resonance, negative charge comes over here. So negative charge is either coming on ortho position or it's coming on para position. Is it coming on this meta position? No, it's not coming on the meta position. So I can simply say hyperconjugation, it does not operate at what? It does not operate at meta position. Yes. Well, let me show you its exact structures. This is structure number 1, where the negative charge is at the ortho position. This is the second structure, where the negative charge came at the para position, right, due to the resonance. Okay, so negative charge is not being generated at the meta position. So I'll say hyperconjugation, it is not being operated at the meta position, right? Perfect. Wonderful. So we will, one more important thing, this plus H effect, right? Plus H effect, it increases the stability of the alkenes. This plus H effect, it increases the stability of alkenes, right? So if you need to compare the stability of the alkenes, you can compare it with the help of hyperconjugation. That's it, yeah? Plus H effect, it increases the stability of the alkene. Okay, now guys understand properly what I'm going to say. It's a very simple thing. See, we have got a double bond between carbon and carbon right here. So is this molecule having any alpha hydrogen? Is there any alpha carbon? No, there is no alpha carbon as such. This would have been, I mean, this I would have called, if it was like this carbon I would have called as alpha carbon because it was attached to the sp2 hybridized carbon atom. But there is no alpha carbon right here. So alpha hydrogens are going to be 0 over here. Yes. Now at the same time, if I ask you how many alpha carbons do we have right here? See, this is sp2 hybridized carbon, and with this sp2 hybridized carbon, this carbon right here is sp3. So I'm calling this carbon right here as sp3 hybridized carbon, and the hydrogens which are attached to this sp3 hybridized carbon are called as alpha hydrogens. So how many alpha hydrogens do I have in this molecule? We have got 3 alpha hydrogens right here. Yes. Similarly, if I ask you how many alpha hydrogens right here, we have got 6 alpha hydrogens right here. I told you in the beginning, more the alpha hydrogens means more the hyperconjugation. More the hyperconjugation means more the stability, right? More the hyperconjugation means more the delocalization. And we already know wherever delocalization is going to be the maximum, there only stability is going to be the maximum. Yes. So which one is going to be maximum stable? Third one is going to be maximum stable, followed by second, followed by first, right? Why is that? Because in the third one, there are maximum alpha hydrogens, due to which there will be maximum hyperconjugated structures, right? Let me know in the chat box if it's clear to you. Let me know fast if it's clear to you so that I can move on to the next thing. Yeah, I mean, I'm doing great. Thank you. Yes? Perfect. Wait, Karthik, wait for that, wait for that. You'll get your answer in a while. Now we will understand. See, if I ask you, does plus H effect apply on carbocations? What should be your answer? Just say yes or no. Just say yes or no. Does plus H effect apply on carbocations? Just say yes or no in the chat box. I'll get to know. Let me know fast. Let me know fast. Does plus H effect apply on carbocations? What do you think? Absolutely yes. Why is that? Understand. If I ask you, what is the hybridization of this carbon? First of all, what is hyperconjugation as per your valence bond theory approach? It is sp3 p overlap, right? This is something which I call as hyperconjugation. Yes. Now people, this carbon right here, it is sp2. It is sp2 hybridized carbon. So right here, can I say there'll be one p orbital with this carbon? Yes. Okay. At the same time, this is sp3. This is sp3 right here. Yes. Can I say there'll be sigma p overlap, there'll be sp3p overlap, and whenever there is sp3p overlap, whenever there is sigma p overlap, can I say that's what I call as hyperconjugation? So right here, in case of carbocations, hyperconjugation is applied. Yes, we can apply the concept of plus H effect, concept of hyperconjugation in carbocations. Yes, right? And what are going to be its hyperconjugating structures if I'll ask you? If I'll ask you what are going to be its hyperconjugating structures? First thing, this bond you are going to break in this direction. Yes, or I think I have made the structures. Let me check. No, let me make these structures. So what are going to be the hyperconjugated structures right here? Can I say, first thing you're going to break this bond in this direction, and this is going to remain as H positive, which is going to remain attached with this, right? Similarly, in the another case, you're going to break this bond in this direction. Yes, and over here you'll see H positive remaining attached in the vicinity of this molecule. Similarly, in the another case, you are going to break this bond in this direction, and over here it's going to be a double bond, and there will be H positive right here attached over here. Yes. So how many hyperconjugated structures do we have in this molecule? We have got 3 hyperconjugated structures. Yes. Right? Yeah. So let me show you this a bit more in detail. So first hyperconjugated structure is going to be like this. So it's going to be carbon, and right here you're going to have H positive, which is going to remain attached. This is one more hydrogen, this one more hydrogen, and right here you're going to keep the double bond, and this is simply your CH2. This is one hyperconjugated structure. Yes. What is going to be the second one? Just break this bond in this direction. So the second one is simply going to be, this is H, and over here you are going to have H positive. Right here there's a double bond, and this is CH2. What about the third one? Third one is simply going to be, this is H, I'm keeping as such, this H I'm keeping as such, and this right here is going to be H positive, right here double bond, this is going to be CH2. So how many hyperconjugated structures are right here in this molecule? I'll say there are 3 hyperconjugated structures. Okay. Remember guys, plus H effect, it increases the stability of the carbocation. As we already knew, when I taught you the inductive effect, I told you plus I effect, it increases the stability of carbocation. Similarly, you can say plus H effect also increases the stability of the carbocation, right? More the alpha hydrogens in the carbocation, more are going to be the hyperconjugated structures, more is going to be the stability of that carbocation. Yes? Right. Let's get to know this a bit more in detail by just having a look on this series. I want you guys to remember this series, okay? This CH3 group, it has got maximum plus H power, followed by CH2D, followed by CHD2, followed by CD3, followed by CD2T, followed by CDT2, followed by CDT3, right? This is something which I want you guys to take a note of, okay? This is the series of plus H, okay? And I'm going to apply this series right here in some time, okay? Now we will have the same time. Remember, mesomeric effect dominates over hyperconjugation, and hyperconjugation dominates over inductive effect. Why is that? I mean, how can I justify this thing? Let me tell you, if I'll be having any molecule in which hyperconjugation is possible, inductive effect is all possible. Right here, let's say I've got a molecule in which 2 effects are possible, hyperconjugation as well as inductive effect. I'm going to give preference to hyperconjugation, okay? If I'll be having any molecule in which there'll be mesomeric effect and inductive effect, I'll be considering its mesomeric effect. So remember, mesomeric effect, it's dominating to hyperconjugation, and hyperconjugation itself is dominating to inductive effect. Yes? Okay? Yes, Priya, absolutely. Now guys, let's talk about the stability order by means of hyperconjugated structures. Understand. See, this is something as CH3 positive. Right here, there is positive charge on this carbon. Right here, there is positive charge on this carbon. If I ask you, what is the hybridization of this carbon? Right here, it's sp2. If I ask you, what is the hybridization of this carbon? It's again sp2. If I ask you, what is the hybridization of this carbon? Right here, it is sp2. Yes. So people, how many alpha hydrogens do we have right here in this CH3 positive? Can I say there is no alpha hydrogen as such? There is no alpha hydrogen as such. Yes. Yeah. People, if I ask you how many alpha hydrogens are in this one, say this carbon is what I call as alpha carbon. With this alpha carbon, there are 3 hydrogens attached. So I'll say there are 3 alpha hydrogens in this one. Yeah. Similarly, if I ask you how many alpha hydrogens are right here in this one, what do you think? So it has got how many? See, first of all, this carbon I'm calling as alpha carbon. Yes. And towards this alpha carbon, there are 2 hydrogens attached. So there are 2 alpha hydrogens. And the number of alpha hydrogens is always equal to the number of number of hyperconjugated structures. Yes. So can I say something like this? Can I say this one has got maximum alpha hydrogens? So this one is going to have maximum hyperconjugated structures. So this one is going to be maximum stable. So 2 is going to be maximum stable, followed by 3, followed by 1. Yes, this is the order of the stability, right? Can you let me know in the next one? Can you let me know in the second one which one is going to be more stable? Can you give me the order of this one? See guys, this is right here sp2 hybridized carbon. This is right here sp2 hybridized carbon. This is sp2 hybridized carbon. Yes. Well guys, the carbon which is attached to this sp2 hybridized carbon, that means I'm talking about this one. This is what I call as alpha carbon. And how many hydrogens are attached with this alpha carbon? There is 1 hydrogen attached with this one. So there is only 1 alpha hydrogen right here in this one. Yeah. Similarly, if I talk about this one, see right here 1 hydrogen, right here you have got 2 hydrogens, correct? So how many alpha hydrogens do we have in this one? We have got 2 plus 1, 3 alpha hydrogens. If I ask you how many alpha hydrogens are in this one, see this is alpha carbon, this is alpha carbon, this is alpha carbon. So there are 3 hydrogens attached right here. There are 2 hydrogens attached right here. There are 2 more hydrogens attached right here. So 3, 2, 5, 7. So there are 7 alpha hydrogens right here. Okay, so third one is going to have maximum alpha hydrogens. Maximum alpha hydrogens means maximum hyperconjugation. Maximum hyperconjugation means maximum stability. So I'll say 3 is the most stable, followed by 2, followed by 1. Yes? Can you let me know if it's clear to every single guy? Can you let me know fast so that I can move on and talk about a few more interesting things? Let me know fast with the thumbs ups. Yeah? Perfect. Perfect, guys, perfect. Let's move on to a few more examples. Let me see what is your answer going to be. Okay, if I talk about these two, okay, can you let me know which one is the, do we have to check the stability order? Arrange the following according to the stability order. Yeah. Can you let me know is the first one or second one? Which one is more stable? I'll say right here we have got 3, 3, 6 alpha hydrogens. Okay. So simply, first one is going to be more stable than that of second. Yeah. First one is going to be definitely more stable than that of second. There are 6 alpha hydrogens. Yeah. People, just let me know in this one, which one is going to be more stable. Let me know fast. Let me know fast. I just want to see it. Let me know. First one or second one, which one is going to be more stable? What do you think? Is there any alpha hydrogen in this one? This is CMe3, right? This is CMe3. This is CMe3, right? Is there any alpha hydrogen in this one? There is no alpha hydrogen in this one. Yes? Correct. In the second one, how many alpha hydrogens do I have? 3, 3, 3. That means 9 alpha hydrogens I have got in the second one. More the alpha hydrogens means more the stability. So second one is definitely going to be more stable than the first one. Yeah. Right? Okay. This is basically methyl group, right? This is methyl. This is Me stands for methyl. This is not a hydrogen. Okay. So 2 is going to be more stable than the first. Correct? So it's basically, if you're getting confused like this, instead of Me3, you can write it as CH3 whole thrice. Okay, instead of Me3, you can write it as CH3 whole thrice. I hope now it's clear. You can write it as CH3 whole thrice. Yeah? Okay? Perfect. Let's move on to a few more things. That's what we call as minus H effect. So till now we talked about plus H effect, which increases the stability of the carbocation. Okay. Now let's talk about something called as minus H effect. Which group is going to show minus H effect? See, your CH3 group, it used to show plus H effect. Your CX3 group, it will be showing the minus H effect. Yeah. For example, have a look. See guys, this is again one more molecule which I've taken right here. See, this is carbon, this is a single bond, and this is a halogen right here. This one more halogen, this one more halogen. I have got a sigma bond right here, and this is the pi bond. Yes. See, halogen is more electronegative than that of carbon, so electron density will lie towards this halogen. So what is going to happen? I'll show this carbon right here. It is sp2 hybridized, so it has got a pure p orbital right here. So they are going to show overlap. So it's going to be again the sp3p overlap as per your VBT. Yes. So people, due to this overlap, due to this sp3p overlap, what is going to happen? That's something which I call as hyperconjugation, right? Whenever we have sp3p overlap, that's what we call as hyperconjugation. So right here, hyperconjugation is going to take place, but in which direction? Have a look. The bond you are going to break in this direction, and this bond you are going to place right here. So what you are going to get? You are going to get something like this. This is your X with a negative charge right here. This is the X as such, this is X as such, and right here you are going to place a double bond, and over here the CH is going to remain as such. This bond you have taken over here, so this carbon would have got positive charge over here, so this is CH2 positive. I'll say this is one of the hyperconjugated structures. Yes. Now what about the other hyperconjugated structures right here? Understand what I'm going to do? Right here, see. One more is going to be like this. See, break this bond in this direction. So it's going to be like this. This is X, and this is X with a negative charge. Right here, you'll place a double bond. Yes, and it's going to be CH, single bond. This is going to be CH2 with a positive charge right here. Yeah. What is one more hyperconjugated structure? See, this one I've drawn, this one I've drawn. There is one more left. That is going to be C. This is X, and right here, put a negative charge on this halogen, so this is double bond, and you're going to keep CH as such. This is CH2 positive. This is one more hyperconjugated structure right here. So how many hyperconjugated structures do we have over here? We have got again 3 hyperconjugated structures. Yes, perfect. Yeah. Now let's get to know few more things. This is something which I've drawn already. Yeah, and this is something which you'll be getting in the Telegram in the form of PDF. So no need to worry about anything. Gagandeep, tomorrow we are going to start the chemical bonding. Yeah. Day after tomorrow, it's again going to be chemical bonding, and after that, it's going to be hydrocarbons. Okay. Right. This week we are going to do 2 chapters: chemical bonding as well as hydrocarbons. Right. Okay. So people, understand right here one more important thing. What is this minus H effect? See, what is going to happen? I have a proper conjugated system right here. This is double bond, single bond, double bond. I mean pi, sigma, pi. This is a conjugated system. And with this conjugated system, I have attached a group CX3. Okay. This is a group which I have attached right here. Okay. If I talk about this is a double bond right here, this is a single bond. So they are going to show overlap, right? It's going to be sp3p overlap. sp3p overlap is what I call as hyperconjugation. Now, which kind of hyperconjugation is it going to show? Is this group going to show plus H effect or minus H effect? Understand. What is happening right here? See, you're going to break this bond in this direction, this bond in this direction, or in this direction, whatever is convenient for you. Okay, this in this direction. So people, if I ask you, is this group increasing the electron density in the conjugated system or not? I'll say this group right here, it is decreasing. It is decreasing the electron density in this conjugated system by the delocalization of sigma bond. Yes. And due to the delocalization of the sigma bond, I'll say electron density in this conjugated system is being decreased whenever I'll be having any group. Which will be attached to a conjugated system, right? And that group decreases the electron density, okay? Due to the delocalization of its sigma bonds, we say that group shows minus H effect. Yes. So people, this group right here, that is CX3, it's going to show minus H effect, right? Absolutely, Karthik, you're right. Okay. Perfect. See guys, CX3 decreases electron density in the conjugated system, therefore it shows minus H effect. As I told you, whenever I'll be having any group which will be attached to the conjugated system, if that group decreases the electron density in the conjugated system due to the delocalization of the sigma bonds, we say that group shows minus H effect. Yeah. Now, minus H effect, it does not operate at the meta position. As I told you earlier, plus H effect does not operate at the meta position. In the same way, minus H effect, it's not going to operate at the meta position. What is the reason for that? See, for example, I've got a molecule right here. This is a molecule. Yes. Now guys, understand. I have got a benzene ring, which is an example of the perfect conjugate system. And with this benzene ring, I have attached the group CX3. Okay. So I have got this sigma and this is pi. okay, sigma and this pi, can I say over here hyperconjugation is possible? Which type of hyperconjugation? Is this group going to show plus H or minus H? It's definitely going to show minus H, as I told you a few minutes back. Yes. So this bond you're going to break in this direction. This bond you're going to break in this direction. So first hyperconjugated structure is going to be like this. This is X, and right here this X is going to have the negative charge. This is one more X, and right here you're going to give me the double bond, and over here what's going to happen, since you have removed the double bond from here, so this carbon is going to get the positive charge, and this double bond as such, this double bond as such. I've done nothing with these two double bonds. Yes. Now guys, understand one more thing. See, once the positive charge is created at the ortho position, can I say over here I got one more conjugation, that is pi sigma positive charge, right? Yes, pi sigma positive charge. Isn't it going to show right here the resonance? We have talked about the conjugations, a lot of conjugations we have talked about. This is one type of conjugation, pi sigma positive charge, right? Okay, so what is going to happen? I'll say it's going to show resonance. This bond will be broken down in this direction, and this positive charge will come over here like this. Let me show it. This is X, this is X, and this is X negative right here. Yeah, this is X with a negative charge right here, and this is the double bond as such. And what I have done, I have broken this double bond in this direction. So there is a double bond right here, there is a positive charge on this carbon, there is the double bond as such. Yes. So people, can I say due to the hyperconjugation, due to the minus I effect of this CH3 group, can I say positive charge is being generated on this position or on this position? Right? Can I say positive charge is being created on ortho and para position only? Is positive charge being created at meta position? Positive charge is not being created at meta position. So I'll say minus H effect, it does not operate at the meta position, right? Yes? Let me know fast in the chat box if it's clear. Let me know fast in the chat box if it's clear to everyone. Yes, I'll be doing that. Yeah? I'm not ignoring anyone. It's a very short and precise session. So I need to finish it off, right? Perfect. Let's move on. Let's talk about some examples. Okay, this is something which I've shown you. Okay, minus H power. Okay, Ci3 maximum minus H followed by Cbr3 followed by CCl3 followed by CF3. This is something which I want you guys to remember. Okay, the series for plus H also, the series for minus H also, both the series I want you guys to remember. Okay, without remembering these series, you are not going to do the questions, right? Okay, see guys, the first question which is on your screen, arrange the following according to the Ka order, right? That means I'm going to arrange the following in the acidic strength. Remember first, acidic strength is directly proportional to minus effect. More the minus effect, more the acidic strength. Simple. More the minus effect, more the acidic strength. Or you can make the conjugated basis of these acids as well. Then you can check the stability of the negative charge on the conjugated acid, which I used to do in the earlier classes. But right here, I don't want you guys to do any sort of those things. Just remember, acidic strength is directly proportional to minus effect. Yeah. And you already know, mesomeric effect, it's dominating over hyperconjugation, and hyperconjugation is dominating over inductive. Yes. So let's get to know which one is going to have maximum acidic strength right here. First of all, right here you've got COH, 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 COH. So COH is my reference. I've selected my reference right here. So this CH3 is right here at the para position. So which effect should I be considering for this CH3? I'll be considering its plus H effect because hyperconjugation dominates over inductive. Yeah. What about right here? Right here CH3 is at meta position. So should I be considering its plus H effect or plus I? I'll be considering its plus I power, right? Which effect for this CCl3? It's right now at the para position, so I'm going to take its minus H effect, right? CBr3, again minus H effect, right? These are CX3 forms, right? These are CX3 forms, and CX3 group always shows minus H, yeah? What about this CCl3 right here? This is right here at the meta position, so minus H effect is not going to operate from the meta position, so it's only going to show minus I effect, yeah? Okay, as I told you a few minutes back, acidic strength is directly proportional to minus effect, yeah? So which one should I be giving the first priority? See, this is minus H, this is minus H, okay? So these two are going to be maximum acidic. I mean, these two are going to be the most acidic as compared to all. Now in these two, which one has got maximum minus H? Okay, right now, a few minutes back, I gave you one series in which the minus H power of CBr3 was greater than the minus I power of CCl3. Yeah, so I'll say if this is 1, 2, 3, 4. So minus H effect of this CBr3 is going to be greater than that of CCl3. So maximum acidic is going to be the fourth one, followed by third one. Yes. And then we have got minus I, so it's going to be the fifth one. And in 1 and 2, right here plus I, right here plus H. Plus effects, they are going to decrease the acidic strength. Okay, now in these two, which one is going to have less plus effect? So I'll say inductive effect is going to be, inductive effect is not going to be considered in front of this plus H, yeah? Or I'll simply generalize it like this. The one which is going to show minimum plus effect, that is going to be maximum acidic. So which one is showing minimum plus effect? That this inductive effect, right? So I'll say second is the one, and at the end, it's going to be the first one. So this is going to be the order, yeah? 4, 3, 5, 2, 1. Can you let me know in the chat box if it's clear? Can you let me know in the chat box if it's clear to everyone so that I can move on to the next one? Let me know fast. Let me know fast in the chat box with the thumbs ups. Okay? Perfect. Perfect, guys. Let's move on then. Yeah? Let's move on. Let's move on to one more question. Let me see if you can solve this one or not. Arrange the following according to Ka order. That means acidic strength order. Again, you have to talk about acidic strength order. Everywhere you have got OH, so this is my reference. Okay. Let's call this as first, let's call this as second, let's call this as third, fourth, fifth, and sixth. You need to arrange them on the basis of their decreasing acidic strengths. Okay. First thing, which effect I should be taking right here? Can you let me know that? See, CH3 right here at the para position, so its plus H effect is to be taken. Yeah. Right here, this CH3 is at meta position, its plus I effect is to be taken. Yeah. Right here, we have got CCl3 at the para position, its minus H effect is to be taken. Yeah. We have got OMe right. We have got OMe right here. Which effect should I be considering for this one? Can you let me know? Isn't it going to be plus M? I hope you remember. This OMe, it shows plus M. Yeah. This OMe right here, which is at the meta position. I told you guys, when I taught you mesomeric effect, I told you mesomeric effect it does not operate from the meta position. So right here, OMe is present at the meta position. So I'm going to take only its minus I power. Yes. So right here, NO2, you're going to consider its minus M. Yes, NO2 is right here at the meta position. Okay. As I told you a few minutes back, acidic strength is directly proportional. Acidic strength is directly proportional to what? Minus effect, right? Now, which one is going to have maximum minus I? Sorry. Not minus I, which one is going to have maximum minus effect? Yeah. So we already know mesomeric effect, that is dominating over hyperconjugation. Hyperconjugation is dominating over inductive. Yeah. So I'll say the last one is going to be the maximum acidic. It has got maximum minus I effect. Sorry, maximum minus effect. Yeah. So sixth one is going to be the maximum acidic, right? So minus M, leave it aside. Do we have minus M apart from this? No, we do not have minus M. Do we have minus H? Do we have minus H somewhere? Yes, we have minus H over here. So it's going to be third one, right? The second priority is given to the third one. Okay, so this one is over. This one is over. This one is over, right? So I'm done with minus M. I'm done with minus H. Now, this one is showing minus I. This is the 1, 2, 3, 4, fifth one. So after 3, fifth one is going to come. So this one is gone. Now, which all are left? I'll say these 3 are left, right? So that one which shows minimum plus effect is going to be maximum acidic, right? So minimum plus effect is shown by the second one. Yes, right? Followed by the first one, followed by the fourth one. Yeah. So how many of you got this order? Can you let me know in the chat box? How many of you got this order? Can you let me know in the chat box fast? Can you let me know in the chat box? I just want to see how many of you got this order. Perfect. Perfect, guys. Wonderful. Let's see if we have more questions or not. Yeah, we have got one more question. Arrange the following according to KB order. We have to talk about the basic strength. Remember, first thing, basic strength is directly proportional to what? It's directly proportional to plus effect. More the plus effect, more the basic strength. That's it. More the plus effect, more the basic strength. And we already know mesomeric dominates over hyperconjugation, hyperconjugation dominates over inductive. Yeah. Now I need to check first which group shows which effect. Right here we have got CH3 at the para position, so it's going to show what? It's going to show plus H. Yeah. Right here, CCl3 at the para position, it's going to show minus H. Okay. This one is going to show, this CH3 is right here at the meta position. It's simply going to show plus I effect. Yeah. And this CCl3, it's going to simply show minus I effect, right? It's at the meta position. Correct? And basic strength is directly proportional to what? It is directly proportional to plus effect. Now, where is the plus effect maximum? I'll say plus effect is maximum in the first one. So first one is given maximum priority. First one is maximum basic. Leave the first one aside. Now, plus effect is in third one. So after this, third will come. Now, in the second and the last one. Okay? In second and the last one. That one which will show minimum minus I, sorry, that one which is going to show minimum minus I power, not minus I power, that one which is going to show minimum minus power is going to be more basic, yeah? Which one is showing minimum minus power? Which one? Should I be giving preference to minus H or minus I? Can you let me know fast? I'll say I'll give preference to the minus I, which is your fourth one, I guess. 1, 2, 3, 4. So this 4, and after this 4, which one is going to come? Second. 1, 3, 4, 2 is going to be the order, yeah? Is that? Let me know if you got it. Let me know if you got it. Let me know if you got it. Simple, guys. Whenever you need to compare the acidic strength, remember, acidic strength is directly proportional to minus power. More the minus power, more the acidic strength. Basic strength is directly proportional to plus power. More the plus power, more the basic strength. Yeah? Remember it from now onwards. I hope this is clear to everyone. So people, with this, your hyperconjugation is done and dusted. So I think all your concepts about the hyperconjugation would have got cleared. Okay? Still, guys, you can go through the session again. You can watch the session again. And if you feel any sort of problem while watching the lecture, you can let me know personally on the Telegram, Instagram, wherever you find me. Yeah? Okay, at the same time, for the ones who have no idea about the NEET 2021 crash course, which we are starting on the actual Vedantu platform, people, the first thing, if you guys are going to get this NEET 2020 crash course, the first and important benefit is you guys are going to get trained by the teachers of your choice if you are getting enrolled in this NEET 2021 crash course. It's completely your wish to select the teacher, get trained by your selected teacher in this NEET 2021 crash course in your physics, chemistry as well as biology, right? Apart from that, we are going to cover your whole syllabus in this NEET 2021 crash course if you're getting enrolled in this, okay? And apart from the course completion sessions, there'll be some extra sessions regarding the time management, how to manage the time, okay? How to solve the questions in lesser time, okay? You'll be getting the amazing tricks and tips to crack NEET in lesser time, okay? And it's going to be a two-way learning interactive platform wherein you can ask your doubts anytime to your master teachers, yeah? And people, no need to worry about the test series, no need to worry about about the mock test, everything, it's a complete package, everything is included right here, okay, in this NEET 2021 crash course. Well, how to get enrolled in this? You just need to click on the Vedantu app. After clicking on the Vedantu app, you just need to click on the NEET crash course. And after clicking on the NEET crash course, if you want me to train you personally in your chemistry, just use the coupon code as WSNEET. And on using this coupon code of WSNEET, I'll be training you personally, and at the same time, you are going to get 30% off. And after 30% off, you guys are just getting it for 7K. Yeah? Perfect, guys. And the next batch for the NEET 2021 crash course is starting on 19th of April. Okay, so do get enrolled in this. Okay, it's definitely going to help you out, right? Okay, so people, there is the link in the description box of the video as well. You can click on the link and you can get added to the crash course from that link as well. But do not forget to use the coupon code as WSNET. And we have got one more link in the description box. That's for the Telegram. Do click on that link, get added to the Telegram group and stay updated about the classes. And at the end, do not forget to like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Well, this was all from my side in the today's session. I'll see you guys tomorrow at the same time, 7:30. And tomorrow we are going to start the chemical bonding. So do not forget to attend that session as well. Okay. So tomorrow at 7:30, I'm going to start the chemical bonding lecture number 1. Till then, you guys take care. Bye-bye. God bless you all and love you all. Bye, guys. Take care.